Welcome to today's presentation on the maximum sum of three non-overlapping subarrays problem. In this session, we will discuss the problem, approach, and step-by-step solution. Let's begin with the problem description. We are given an array of integers and a number k representing the size of each subarray. The task is to find the indices of three non-overlapping subarrays, each of size k, such that their combined sum is maximized. For example, for the input array 1, 2, 1, 2, 6, 7, 5, 1 and k equals to 2, the optimal subarrays are at indices 0, 3 and 5. To solve this problem, we will use the prefix sum technique to efficiently calculate the sum of any subarray. We will also maintain two helper arrays, the left array, the right array. The left array which tracks the index of the maximum sum subarray to the left of each position. The right array which tracks the index of the maximum sum subarray to the right. Finally, we will iterate through potential middle subarray positions to combine with the best left and right subarrays. Step 1 is to calculate the prefix sum. This allows us to calculate the sum of any subarray in constant time. The formula is simple. Sum ij equals prefix j minus prefix I. We build the prefix sum array where each element represents the cumulative sum of all the elements in the original array up to that point. In step 2, we build the left array. The purpose of this array is to keep track of the starting index of the maximum sum subarray to the left of each position. We initialize the first element and then traverse the array. For each element, we check if a new subarray sum is larger, and if so, we update the left index accordingly. This helps us efficiently retrieve the best left subarray at each position. Step 3 is similar to step 2, but for the right array, this array keeps track of the starting index of the maximum sum subarray to the right of each position. We initialize the last element and traverse the array from right to left, updating the right array whenever we find a larger sum subarray. Now in step 4, we combine the subarray. First, we iterate over all possible middle subarray positions. For each position, we use the left array to find the best left subarray and the right array to find the best right subarray. We calculate total sum of the three subarrays, and if the sum is larger than the previous maximum, we update the result. In the second part of step 4, we complete the combination process by adding the sum of the right subarray. If the combined total exceeds the current maximum, we update the maximum sum and store the resulting indices. Let's now analyze the time and space complexity of our approach. The time complexity is big O of n for building the prefix sum, left and right arrays, and for combining the subarrays. Thus the overall time complexity is linear, that is big O of n. As for space, we use three arrays to store the prefix sum, left, right indices, resulting in a space complexity of big O of n. Here's the first part of the complete code. We initialize the prefix sum array, then build the left and right arrays. This part efficiently sets up the framework for combining the subarrays in the next step. And here's the continuation of the code. After setting up the left and right arrays, we iterate through possible middle subarray positions to calculate the maximum sum and store the indices of the three subarrays that provide this sum. To conclude, in this presentation, we have covered the problem of finding the maximum sum of three non-overlapping subarrays. We explored an efficient approach using prefix sums and helper arrays, followed by a detailed implementation and complexity analysis. This method ensures an optimal solution for the problem. Thank you for your attention.